Okay, so this is another Mathfolio video. This time the topic is for exponents and radicals. This is a review lesson, so please see the specific math lessons that I've done for each of the exponent laws and also for simplifying radicals as well. For today, the review sheet can be downloaded at mathfolio.com/alg1/exprad. Okay, so this is question number 1 from this assessment, this worksheet that I recently gave my own students. Okay, so here we are asked to basically simplify these exponents. So the first thing that we notice is they have the same base. So because they have the same base, that means that we can use the law of exponents. The law of exponents here is going to be the multiplication law. So if we spot that, then one thing that we can do is just recognize that when we're multiplying the same base, we just add the exponents. So we can go straight to x to the 5th. That's the answer. No more work needs to be done. That's the answer. If you want to take a look at the extended piece of work as to why this is true, you can see that if I write it over here, x squared times x to the 3rd, this is really the same as saying x times x, which is x squared, and x cubed is x times x times x, and then we're multiplying both of these quantities together. So if we take a quick look, we've got how many x's here? We've got 1, 2, 3, 4, 5. So therefore we are finally multiplying x by itself 5 times. Same answer each way we look at it. This is the work behind this multiplication law of exponents. Please remember, when you're multiplying and you're using the multiplication law, you are in fact adding the exponents. You are not multiplying the exponents here. Also, remember this only works when the bases are the same. Okay, question number 2. This time it's the division law, and so what we have to do is we do both t, so it's the same base, so we can use the laws, but now we have to subtract the exponents. This is going to be t to the 5 minus 2, which is t to the 3rd, and if we get this far, again, we don't need to do any extra work. However, if you want to look at the reasons behind why this division law works, we have t to the 5th divided by t to the 2nd. Now, I'm going to write this in a slightly different way. I'm going to write it as t on top, t to the 5th over t to the 2nd. Same exact operation that's happening, division. However, this allows me to expand what's going on. T times t times t times t times t. 5 t's on the top, and we're dividing by t times t on the bottom. So in fact, what's really happening here is that a t cancels for a t cancels for a t, and as you can probably see by now, we are left with 3 t's. So we've got t multiplied by itself 3 times. We get the same answer. So this is the reason for the division law and why it works. And let's just remember the division law only works when we have the same base. So here we've got t and t. And remember the division law, we in fact subtract the second exponent from the first exponent. And it must be in that order. So please do not divide the exponents. The division law of exponents means that we subtract the exponents. Okay, so that was question number 2. Here's number 3. Again, there's a law for this as well. This is going to be the power law of exponents. So here, when you've got a number on the outside, you multiply it by the exponents that you see, or even if it's an invisible 1, you would multiply it by any exponent on the inside. And so this would give us an answer of p to the 12th power. To see the expanded reason as to why this is true, if you've got p to the 3rd all to the 4th, what this really means is, well, p to the 3rd is p times p times p. That's p to the 3rd. And if we're doing this to the 4th power, it means that we have to multiply this quantity by itself 4 times. So p times p times p, p times p times p, p times p times p. So this is really what p to the 3rd to the 4th means. We've got p to the 3rd in each of these, and because it's to the 4th, it means we're multiplying it by itself 4 times. So if you look across and you add up how many p's are actually multiplying themselves, we've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got p multiplying by itself 12 times. As you see, it's the same result as we get if we just remember the rule that we multiply the exponents. And again, this is the power law of exponents. Okay, question number 4. This is similar to the power law. The only difference is that inside of the parentheses we've actually got a product inside. So this is called the power of a product law. We've got all this product, we've got 3 to the 4th times y to the 3rd. So remember, when we're multiplying quantities, that gives us a product, and that's all to the 2nd power. So here the rule is, as I say, similar to the power law. We take the exponent outside, we multiply by each of them inside. So this would become 3 to the 8th y to the 6th power, and that's as far as we can go. We could do 3 times 3 times 8 times, but this is good enough right here. We don't really need to go any further. And if you want to look at the reason why for this, because we've got 3 to the 4th y to the 3rd, if I write 3 to the 4th like this, that's my 3 to the 4th, and then y to the 3rd would be y times y times y. So here I've got 3 to the 4th y to the 3rd, which is the same as what's inside of these parentheses. And if I'm squaring this, it means that I'm doing the whole thing again. 3 to the 4th y to the 3rd. Remember, everything's multiplying here, so I could just even drop these exponents right now. But if we count the number of 3's, we've got 8 of them, all multiplying. So 3 is multiplying by itself 8 times, and y is multiplying by itself 6 times. So again, we get the same answer, just much quicker if we remember the laws of exponents. We get straight to the answer. Okay, number 5, this is showing 1.5 to the 0 power. So the quick way to remember this is that anything to the 0 is 1. So you could have 100 to the 0 power, it's 1. You could have 1 to the 0 power, it's 1. You can have 1/2 to the 0 power, it's 1. It does not matter what it is. If you see a 0 power, the value of that is 1. And one way to look at this is if we look at 2 to the 3rd, and then 2 squared, and 2 to the 1st, and we look at the pattern that's going on, well, 2 to the 3rd is, let me just write the numbers next to them, 2 to the 3rd is 8, 2 squared is 4, 2 to the 1st is 2, and if we look at the pattern that's going on between these numbers, we're in fact dividing by 2. We're dividing by 2, so to get from 2 to the value of 2 to the 0, when we divide 2 divided by 2, we would in fact get 1. And this also, we can look a little forward as well and think, well, what happens when we have 2 to the negative 1 if we continue this pattern? Well, again, we would continue by dividing. Let me undo that. It looks a little like a plus right now. You know what? Let me just erase it out of the way. In fact, that's going to be a little better. Okay, so we're looking a little ahead, but if we do 1 divided by 2 to get the value of 2 to the negative 1, then 1 divided by 2 is 1/2. So this is a little clue as to what's coming in some of the other questions. Okay, so that was question number 5. Okay, question number 6 is here. It says simplify 12 to the 1st power. Again, this is another really quick rule, just as we've shown with the pattern on the last slide. 12 to the 1st is just 12. Anything to the 1st power is itself. That's just the rule. We're not timesing it by itself 2 times or 3 times or 4 times. We just have the number. It's to the 1st power. And even if you are given a number 5, not only does this 5 have invisible decimal, invisible zeros going on forever, but it also has an invisible exponent. It has an invisible 1 up there. So keep in mind that every number that doesn't show an exponent actually has an invisible 1. Okay, let's take a look at number 7. Okay, so in number 7, we are asked to write the following in exponential form. So I see some K's, I see some M's, and I see a J. So K is multiplying by itself 6 times. M is multiplying by itself 3 times. And of course, after we get the K's all multiplying, that's in fact multiplying by the M. So we can just write them next to each other. And the J is multiplying by itself no times. It's just there on its own, so it's got an invisible 1 next to it. And in fact, this is our answer for writing this expanded expression in exponential form. Okay, so that was number 7. Number 8, so here's where we have a negative exponent. So things to be careful of are exponents of 1, knowing that that means itself. Exponents of 0, knowing that that just gives you an automatic answer of 1. And then negative exponents and fractional exponents. So this is a negative exponent. So let's really just focus on what's going on here. The way that I teach this is just take a look at the negative. Let's just take that out. So if we take out the negative, we have 3 to the second. Now, we've got to put that negative back, but let's turn it around so it looks like a 1. Put it up there, and then just make a fraction line. That's your answer. 3 to the negative second is really 1 over the base with the positive exponent, so it's 1 over 3 to the second. You could also simplify this to 1 over 9. This would be a preferred answer in this case, but both of them are correct. And you know, just remember what happened with these 2's when we got to 2 to the second, 2 to the first, 2 to the 0, 2 to the negative 1, 2 to the negative 2. If you see that the values here of these numbers are 4, 2, remember we said 1, anything to the 0 power is 1, then really what's happening is we are dividing by 2. So 4 divided by 2 gives you 2. 2 divided by 2 gives you 1. 1 divided by 2 gives you 1/2. 1/2 divided by 2 gives you 1 over 4. And so even if we just focus on this very last one very quickly, if you've got 2 to the negative 2, that would be stare at the negative, take it out. You'd have 2 squared left, and then put the negative back as a 1, turn it around, put it as a 1, and then make a fraction line. So these are the same thing. 1 over 2 squared is the same as 1 over 4. And so the pattern shows us that what we're doing is completely correct. So that was number 8. Okay, number 9. Right, so here we've got a fractional exponent. So this is where the world of exponents meets the world of radicals. And so when you have a fractional exponent, and here it's 4 to the 1/2, what happens is that this we can write as radical 4 with an index that's the same as the denominator. So it would be a 2, and of course when it's an index of 2 we just show it as square root of 4. So this is one of the answers, square root of 4. Let me put that up there. So remember that anything to the half is really taking the square root of that number. And then the square root of 4, in fact, equals 2. So we could just write the 2 there. So these three things are exactly the same. 4 to the half is exactly the same as square root of 4. And of course, that's exactly the same as 2. So that's our answer to number 9. Okay, number 10 is asking us to simplify these radicals. And this is the next 4 questions, in fact. So let's take a look at number 10 itself. So we're given, and really didn't come out on the print, but really this should have the roof over the top. So let's just put that on. This should have the roof on top of both of these. So square root of 200. Now, ideally what we can do is try and think of perfect squares that are factors. So 100's a perfect square, and 100 definitely goes into 200. This becomes 100 times 2. Now, what we can do is give each of these numbers their own umbrella. So I'm calling the radical sign an umbrella, but just bear with me. So now we've separated them. We're allowed to do this as long as they're multiplying or dividing. We can give them their own umbrella. If they're being added or subtracted, we cannot do this. Okay, in this case, 100, the square root of 100 gives you 10. Square root of 2 we can't really do anything with, so then we leave that as 10 radical 2. Now, a couple of things to keep in mind. This is not the same as radical 2 with a base, with an index of 10. This is not the same, so this would be incorrect if you put the little 10 there. Another thing to keep in mind is that simplifying radicals means trying to get as many of the factors out from underneath the radical itself by reducing the size of the number that's being square rooted or cube rooted or whatever. And we can only do that by bringing out perfect squares and square rooting them on their way out. Now, one other thing to notice is that if you didn't do 100 times 2 straight away, that's not such a big problem. Let's look what would have happened. If you got 200 equals, and then you just kept going and going and going. So let's just say we said 50 times 4. And then we saw that, well, really 50 is 5 times 10. And we saw that 4 is 2 times 2. And let's say that then we also kept going and we saw that, well, we could write this as 5 times, well, 10 is 2 times another 5. And then we still have our 2 times 2. And at this point, what happens is that we could now give them their own umbrella, radical 5, radical 2, radical 5, radical 2, radical 2. So notice what we've done. We can't break these down any further. These are all prime factors. But now this is where kind of like the fun bit comes. If we've got radical 5 and we times by radical 5, what this gives us is the 5 back. If we've got let me change this color right now. Let me go over to orange. If we've got radical 2 and another radical 2 and we multiply those together, then we get the 2. So keep in mind this is 5 times 2 times. Now the leftover here is in fact just the radical 2. So if we just bring that down, then we could actually now see that we have very close to our answer over here. And in fact, we're going to get that answer. When we do 5 times 2, we get our 10 back, so that becomes 10 radical 2. So we get exactly the same answer, just it took us a lot longer. If we can see that 100 is there straight away, 100's a pretty big perfect square. We can square root that and pull that away from the radical sign straight away. Okay, so let's try and find the biggest perfect square that's a factor of 80. Well, I know that 5 goes into 80 16 times, so therefore 80 is really 16 times 5. And we must keep the radical sign. And this is a nice factor to find for 16, because when we separate the umbrellas, we've got radical 16 times radical 5. And of course, the square root of 16 is 4. So this becomes 4 radical 5. And that's our answer for number 11. And keep in mind again, this is not the 4th root of 5. We do not want to show a 4 as an index here. This would be absolutely incorrect. The 4 is a whole number that's multiplying the quantity of square root of 5. So that's our answer for number 11. Okay, so number 12 is here, so let's try this one. Number 12 is saying the square root of 30. Well, I'm not sure if we're going to be able to pull out a square root factor here. So let's see. Well, if we break 30 down, and you can also use prime factorization as well. We could say 5 times 6, and then 6 would break into 2 times 3. These are all our prime numbers. So 30 is really 5 times 2 times 3. So it actually doesn't even matter if we give them their own umbrella. There's nothing that we can remove and extract from underneath this radical. And because there's no single digit here that we can, or no single number here that we can square root, basically we've got to leave our answer as the square root of 30. That's as simplified as it gets. So if this is confusing you a little, think of, if we were given 3 over 6 and told to simplify, we could simplify this to 1/2, divide by 3, divide by 3. But if you were given 1/2 to begin with and told to simplify, you can't. It's as simple as it gets. So 1/2 would be your answer. Okay, now radical 120 isn't the same because 4 goes into it, and 4 is in fact a perfect square. So we could rewrite this as 4 times 30. And once we give them their own umbrellas, we've got radical 4 times by radical 30. And of course, radical 30 we know from down here, we can't simplify that anymore. But square root of 4 is 2, so our answer is 2 radical 30. That's our answer for number 13. Okay, number 14. Number 14 is asking us to simplify this monomial divided by this other monomial. So one thing that I'm going to do here is I'm going to write them with the division line. So I've got 16 m squared n cubed p, and this is divided by, now I'm going to line things up. I'm going to put the 8 under the other number. Got the m, which is here, and this m is really to the first power. The n is also here to the first power, and there isn't a p. It's just this. So now when I go through this, I can do 16 divided by 8, and that gives me 2. I can do my m squared divided by m to the first, so this is now the division law, so I'm going to do 2 minus 1 for the exponent. This is going to be m to the invisible 1, so I'm just going to leave that. N cubed divided by n to the first is going to be n squared, and p divided by like 1, p divided by nothing really, it's just an invisible 1 there, is just going to keep my p. And if this is a little confusing as to why I keep that p, you could also, so try and focus on this a little, you could also think of this, well sure, this is p to the first, and I'm not changing it if I write p to the 0 underneath, because p to the 0 is 1. So dividing p by 1, even though I'm writing 1 as p to the 0, I'm not really changing it. So therefore, to do this division, we could use a division law. It's p to the first, and then subtract 0, which gives you p to the first, which is just p. And so this is my answer for 14. Okay, number 15. 15 should be a really quick one. And so what we're doing here is we're multiplying the same number. We're squaring the square root of 7.1. So whenever you see something like this, you should always think that the inside number is going to pop out, and it does, 7.1. One way to look at this is to think, well, this is the same as writing 7.1 to the 1/2. Remember that half is the same as square rooting, and we're timesing this by, same again, 7.1 to the 1/2. So the multiplication law of exponents would say, well, it's the same base, so you just add the exponents. So we're going to do 1/2 plus 1/2, which is then going to give us 7.1 to the first, which equals 7.1. That's one way of looking at this problem as well. But if you just see it straight away, just write it, 7.1. Okay, the final question here. This is the bonus question. So this is a little tricky, but let me just write it a little bigger. So we've got 225 m to negative 4 n to the 5th, and this is all over 15, so I'm going to write my 15 over underneath the 225. M to the second, there's no n, so I'm going to leave a gap, and then I'm going to write p to the negative 3. Now, what caught a lot of people out in a recent quiz that I gave was this, even though students knew that p to the negative 3 is the same as 1 over p cubed, because this is the denominator of this fraction, of this division problem, something a little weird happens. So let's take a look. So for the number part right here, 225 divided by 15 gives me 15. So we dealt with the numbers. M to the negative 4 divided by m to the second, m squared, we're going to subtract. So negative 4 minus 2 gives me negative 6. The n to the 5th is really just dividing by 1, which is n to the 5th. And then this is really a 1 over p to the negative third. So one thing that I can do is keep my p to the negative third on the bottom. Now, let's really think what's going on here. This is a good answer so far, but because this m is to the negative 6, we could also, let me just switch colors for a second, I'm going to go to orange. We could write this as 15 times by, now m to the negative 6 is really 1 over m to the 6. N to the 5th would stay on top. Now, because we are dividing, that's what we're doing right here, we are dividing by p to the negative third. And so really what we're doing is dividing by 1 over p cubed. Now this is the same as multiplying by the reciprocal, p cubed over 1. So if we see that, this p to the negative 3 on the bottom could become p to the 3 on the top. So when we piece all this together and we do the multiplication, we got 15 times 1, which is 15 times n to the 5th, which we keep, times p to the third, all over m to the 6. That's our answer for the bonus question in its simplest form right here. Okay, so that's the end of this review for exponents and radicals. This is a really important topic, and math just builds on here in high school, so it's really important that you understand these concepts. This was a review, so I kind of went very quickly through these questions. You should definitely go back, search on my YouTube channel, Mathfolio, for individual lessons on each of the laws of exponents and on simplifying radicals and on those special rules. If you're watching this on YouTube, please subscribe and maybe leave a comment. Thanks again.